has to has to has to be the account holder on the Zoom first of all.
Okay, good.
If you don't have the account on the Zoom, then Zoom will not allow you to enter into this meeting.
Good. So, what are your experiences with the previous presentations? It went well?
Yes, sir. Previous lectures went very, very well. Only this last one, 3 days ago, there was an interruption in the internet connectivity, probably from Romania.
Okay.
So yeah, so, but that can happen anytime, anywhere.
Yes. So hopefully everything is running well today.
Yeah. I hope so. Yes. And one more thing, that we have not asked any separate for any separate registration. So registration is done right in the Zoom, and the data we retrieve of all the registration. So at the end of the lecture, we retrieve the whole Excel sheet of all the data of the participants.
Okay, good.
So there is no separate registration kind of thing. Yeah.
And you are also planning now a summer school to be held next year in Bosnia. Is
Yes,
that right?
Correct.
Yeah,
Correct.
okay.
Correct.
Okay.
So our organizing committee, actually, we had a meeting just some days ago, and they have been worried for this because of this troubles in Ukraine.
Yes.
So,
Problems
yeah.
about the war. Yeah.
Particularly, the program is global, and the foreign participants have to come. Therefore, the not all people can be confident to join in Ukraine. So that's why we have decided to shift it. Yeah. So, sir, you please test whether your presentation is working or not. You just share the screen and just test it first.
Okay, so let me see. I will use this screen. I think this one maybe.
Yeah, it's working, sir. So we can close it for some few minutes, and then after that you can restart.
So you see now
Yeah,
the starting transparency.
yes,
The
yes.
first one. Okay.
Yeah.
Okay. Good.
Yes. Just please close it for a few minutes. Yeah, thank you.
And when do we start at 10, I guess? So?
Yeah, it's time is now. Yeah, we can pick it. So just to I request you to wait a minute, 1 minute only. Yeah.
And I should introduce myself, or you will do that. So
Yes, sir. I will brief about it, just a bit brief about you, because I have not read very much about you at the moment. I'm sorry,
yeah.
but I will just introduce, and then you will add more about your work and your past achievements. Yes. So let's begin. Yeah. Professor Hans Peter is with us, my dear friends. and he is Professor Emeritus. Um, yeah, let me, yeah, at the University of Natural Resources and Life Sciences, Vienna, Austria. He is with the Institute of Water Management, Hydrology and Hydrological Engineering. So he is one of the rare experts in the water sciences and engineering and technologies. He has written a number of books on this subject, and obviously a long list of the publications, very renowned scientific publications he has in his credit. So I'm sorry I have not read, and I was really not ready to introduce him, but uh, I was expecting that some very senior person will introduce him anyway. So I request him to tell about himself a little bit more. Although his CV and his all written achievements are already on the website, so we have the link on the detailed page of this particular lecture on the website, so you can just browse some data about him. There's a lot, even if you can search by his name in the Google, and you will find a lot literature about him. So thank you, sir. I invite you to this lecture on this particular topic. It's very specific topic you have proposed today, and we are sure that all the audience and scientists present in this online forum will benefit from your rare knowledge and your experiences in the continents, I should say. So thank you so much for joining us, and now I hand over to you. Thank you, sir.
I thank you. So let's see if it's working. Yes. So I hope you can see my transparency. 1 second. Yes. So welcome, everybody. I'm very pleased to contribute to this series of lectures. I'm based here in Vienna, Austria, so it's 10 o'clock in the morning. So welcome everybody, and let me add a few words about my background. So Hazrat has given a general introduction about myself. So by education, I'm a physicist. I started physics at Technical University Vienna, and I did my PhD in physics about semiconductors, etc. I enjoyed it very much, but I realized I'm going to lose somehow contact with nature. So I thought about alternatives, and then I moved to the University of Natural Resources and Life Sciences, and I visited and came in touch with the Institute of Water Management and Hydrology, and I've been working there for a pretty long time, became head of the institute, and now I'm retired. So this is very briefly. Today I would like to speak about, on one side, climate change, on the other side also about our direct interventions into the water cycle. And to my opinion, our direct interventions are at the moment really very serious, and sometimes we blame also a little bit on climate change issues, although we are directly intervening. But it's up to you to assess this. I tried to provide some background information. That's one part of my story. And the other one refers to, well, when we live in a dynamic environment, then we have to think about our approaches. And so I try to show that our environment is really quite dynamic. And on the other side, I'm thinking about the methodologies we are using if we take decisions. So, summarizing, I try to provide some information to enable us to discriminate among external impacts and internal forcings. And this holds for both the climate and our water resources system. And also the problem of scales, time scales is underlined, and then how to make decisions in a dynamic environment. And this leads immediately to the structure. So I'm an engineer. I'm considering myself as an engineer. We need to take decisions. We need to design something. We need to manage systems, and how we can take actions and decisions in the case when we are exposed to external forcings and internal forcings. And how can we really act? So this is, in a brief, in a nutshell, what I'm trying to present. What are the main tasks of an engineer like a hydrologist or a water manager? In principle, we have to satisfy human water requirements. And this means, due to the external variability in our environment, we need to balance in space and time these variabilities. And also, we need to reduce external shocks like floods or the extreme drought periods. So usually we have some time series of observations, rainfall, runoff, temperature, whatever you have in mind. Depends on the region, depends on the scale also, but I would say something like 50, 100 years of observations are in general in a wider region available. So we look back, we analyze this data, and we fit the model. And model fitting is we adjust parameters to describe what we have observed in the past. That's nice. And then we make predictions and we provide design values. But we should be aware that our data go back to something like 50 or 100 years. And then we use this information and these fitted models to think about the future. Somehow we can say we assume a steady environment. And when you think about design, well, usually we design something for a lifetime of about 100 years. But when you think about, for instance, safety measures like a spillway in a dam, or when you think about designing a levee, well, you end up at, well, something like 5,000 years floods, 10,000 years floods, depends on the problem. Levee is designed for, let's say, 100 years, but a release structure is designed for a much larger period. Okay. In reality, we realize that we are exposed to changes which can be described by cycles, seasonalities, by shocks, and also by internal buffering mechanisms. And when we think about what we have really observed in the last very few centuries, we can briefly summarize losses in fertile land, increasing pollution of the environment, increasing pressure on natural environment. And all these impacts can be described by a set of indicators which would clearly document that. So we disregard somehow, as I tried to show previously, that we are exposed to cycles, trends. And now I would like to analyze some of these trends and cycles. So let's think about climate and let's think about direct human interventions. So we observe, that all increasing temperature, increase of greenhouse gases due to our activities. But at the same time, we have volcanic activities, we have long-term changes due to internal terrestrial processes, we have external forcings, changes due to solar irradiation. And at our globe, population growth, severe land use changes, we intervene into the water cycle at many, many levels, and we release pollutants to our environment. I was somehow surprised. A few years ago, I met a scientist and he told me, well, he was a geologist, by the way, but he mentioned, well, he has some criticism about climate change issues because we speak about ppm's changes in the atmosphere. So he was not sure about that. And I was surprised about that. But as I told you, I'm a physicist, so Fourier, about 200 years ago, and later on it was confirmed by measurements, and then it was fully quantified more than 100 years ago, proved that the greenhouse gas effect is responsible for our temperature conditions at our globe. Without greenhouse gases, the mean global temperature would be substantially lower. And this means, on the other side, due to activities, human activities, we observe an increase in greenhouse gases, and therefore we observe an increase in temperature, glacier melt, sea level rise, and all these consequences. Let's go a little bit more into detail. Mostly I used the data from the previous IPCC report. A few months ago, a new IPCC report has been released. So this refers to the last but one increase here in temperature based on different data sets, but in general, we cover here a period from about 1850 to recent conditions. And these are the decadal averages, again, based on different data sets. Both of them, or all of them, show a clear increase in temperature over the last decades. This is about 150, 170 years. When we look back for a longer period, we have here the period from about the last 2,000 years. And you see here changes in greenhouse gases. We have CO2, we have methane, and we have N2O over a period of about 2,000 years. And all of these data indicate, well, since about 1850, there is an increase in all these greenhouse gases. That's one side. These data refer to samples from boreholes and analysis of stalagmites. There are different ways to reconstruct longer periods. So this is somehow based on observations. When we compare that, then we can see that all what we observe today, so the present state of greenhouse gases, exceeds the range of all what we have observed over the last 800,000 years. And today we have concentration in greenhouse gases that is also exceeding all the data which go back about 800,000 years. And the last period with respect to temperature from about 2000 to about 2010 was the hottest decade since the last 2000 years. So this is greenhouse gases. That's one part. But we have also interactions with internal processes like volcanic activities. And this is associated with emission of high amounts of CO2, SO2, etc. And here you have a small list of events which have been reported for the last about 20 years. There are different processes, don't want to go into detail, but when we compare it with the impacts on the atmosphere, well, you can find some data here from the IPCC report. So all these events which we see here, different models have been used to reconstruct all this data. They are related to reduction in the incoming energy due to emission of aerosols, etc. These are two reconstructed time series of volcanic forces. So, compared to this, you have here the unit in watt per square meter, changes in radiation energy balance. Here you have the variability, short-term variability with respect to solar activities. We will discuss it in the next slides, but only have a look on the scale here. It's also total solar irradiation expressed in watt per square meter. It's much smaller than what we have found here in the data due to volcanic eruptions. Now, let's look on external forces. And here we have the traditional image, the sun in the center, and then we have all these well-defined paths of the planets around the sun, and it looks very nice. And the cosmos is the name cosmos and cosmetics. Cosmos is beautiful, well organized, well structured, well defined system. Order in the sky, cosmos in the sky, chaos on our globe. But it's not really like that. It's slightly different. And let's have a look on that. And this refers to the Milankovitch cycles. And Milankovitch, I think it was 2 years ago, that there was a conference in Belgrade to celebrate Milankovitch birthday. So let's have a look on the movement of the Earth around the sun. Sometimes it's close to a circle, and sometimes it's more elliptic. And this changes permanently. And this orbital eccentricity has a cycle of about 100,000 years. So it's permanently changing and moving, but a cyclic behavior. Then we have obliquity. So the inclination of the rotation axis of our planet is also changing. And this cycle is about 41,000 years, obliquity. And then it's not really a change exclusively in the inclination. Also, the axis of our planet is also rotating. And this is a cycle of 26,000 years. And then we have abyssal precession. So the movement of our planet around the sun is also changing in the long term, like that, with a cycle of more than 100,000 years. So this is pure movement of the Earth in around the sun and internally with respect to the various instabilities. The most dominant factor with respect to climate is the obliquity. And it's changing between 24 centigrades, minimum is 22 centigrades. And when the inclination is higher, this implies that more energy hits the area north of 60 centigrades. And then it's getting warmer globally. If the inclination is smaller, then the ice caps are being formed and glaciation starts. And this is a permanent process with the cycles. We will discuss it later, and we have already seen. But this is only Earth, our world, the sun, and the moon. Additionally, there are orbital forcings by other planets, and this means there are some additional periodicities found in our movement of the Earth. And as I said, obliquity is the most dominating one with about 40,000 years cyclicity. And this is mainly responsible for glaciation and deglaciation processes. This has been also confirmed in the IPCC report. There is high confidence that orbital forcing is the primary external driver of glacial cycles. And there are some additional internal feedbacks. Further, we have also cosmic forcings due to solar activity. Previous part related to the movement, so the mechanical structure. Now we briefly have a look on the solar activity itself, irradiation, that's also changing, and several cycles have been detected with different periodicity, ranging from 11 years, typical sunspot number changes, going up to 2,200 years, so-called Hallstatt cycles. The impact of these activities are considered as very small with respect to our climate. And now let's compare these different external drivers. These are the changes of the anomalies expressed in centigrade, so anomalies in global temperature. You have here a period from about 1870 to about 2010, and this is the volcanic component. Have a look also on the scale here. So volcanic impacts are obviously happening. They can be measured and detected, but they are limited for maximum 2 to 3 years. What has happened in the past. Here you have the solar component over that period, and you see these cycles. They are rather small here compared to this volcanic impacts. Then we have the internal variability due to feedback mechanisms. Think about El Nino effects, think about the conveyor belt in our oceans, etc. And here you have the anthropogenic component. And obviously, the anthropogenic component is by far greater than all the other ones. And when you add up these 1, 2, 3, 4 components, you get the red line. And this is the anomaly in global temperature, measured the black line and red line, the reconstructed changes in anomalies. So obviously, the models are quite able to describe what we have observed in the last 130, 50 years. And when we assess these drivers, we can conclude the mean global surface temperature increase for this period is about 0.87. So let's say 0.9. The increase can be well explained. We have discussed that the volcanic contribution is about 0.1 to 0.2 for shorter periods. So anthropogenic impact is about more than 0.8 centigrades for that period. What we have observed during larger time periods, several 10,000 years, temperature may vary between plus 1.5 and minus 8 centigrades. So this is the variability at very large time scales. What we have observed in 100 years is about 0.8 centigrades. So during deglaciation periods, temperature increase was about 0.3 to 0.8 centigrades, maximum 1.5 centigrades per 1,000 years. The changes in CO2 concentration varied between 180 to about 300 ppm. Today, it's more than 400 ppms. When we take the anthropogenic effect of greenhouse gases, we would receive a temperature increase of about 6.3 degrees per 1,000 years. Compare that with the number due to, let's say, natural processes. So it's much larger, much faster than what we have observed in the past. Of course, all these climate changes have direct impacts on the water cycle, and usually we could assess these impacts, changes in the mean. It will get drier, it will get wetter. We could change it in the variability. Very often we analyze changes in extremes, but we should also think about persistence. What does it mean? So if a certain state is being observed, how quickly would it change? This can be described by indicators like persistence. But now we would like to look ahead. This is now what has happened in the past. But we don't know how and how quickly global transition will be managed, if it will be managed at all. Think about changes in economy, technology, political problems, etc. Thus, we try, when we speak about the future, to characterize the future by different scenarios, what may happen. And these are the scenarios which are usually applied for climate change impact studies. So this would be the worst case RCP85 scenario. This would be the green revolution, where we reduce the CO2 emissions as good as possible. And this is the range of outcomes due to different scenarios. No one can really tell what would really happen, but we are already here, and not too much actions have been taken to cope with global problems. And this would be the respective changes in mean global temperature. And you see already by 2050, we have quite a broad range in increases. And last week, you could read in newspapers that very likely we will not be able to manage the 1.5 centigrade increase in temperature. Very likely increases will be larger. So these are the different scenarios, and this is the range due to uncertainties with respect to data, with respect to models. But you can clearly see that there is a quite broad range in outcomes dependent on the scenarios we are using. What are the consequences with respect to water-related issues? I don't want to go into detail. You find a lot of maps and data, but let's start with Europe here. These are the expected increases in temperature up to the period 2070 to 2090. This has been taken from the Prudence project. So you see, when you are closer to the oceans, the increase is somewhat smaller in temperature. In the continental areas and in the alpine areas, the increases, mean annual temperature, are expected to be more pronounced, about 3.5 centigrades. And these are the expected changes in precipitation. In general, we could say south of the Alps, it will get drier. North of the Alps, it will get somewhat wetter. Second, this would be the change in the mean. Think about the changes in the variability in extremes. And here, this is a work which has been published in 2013, characterizing changes in 100 years flood event. And the colors indicate that in those areas where we observe blue colors means there will be more floods, or 100 years flood will be more frequent. In the yellow and red areas means 100 years flood event will be less frequent. So would become, for instance, when you think about Europe, 100 years event, it is expected that it will be by the end of this century, something like 150 to 250 years. Here in the blue areas, 100 years flood would be more frequent, would occur with a higher or shorter time interval, let's say 25 to 50 years. And think what we have discussed at the beginning. We design something for the future. We speak about 100 years flood. We speak about even 1,000 years flood and beyond. And these are the changes we expect in the next few decades. So this was climate. Now let's have a look how we intervene in the water cycle. What are the direct human interventions? And I'm going to use a few examples, but first I would like to describe where we intervene. We intervene in the land use. Wherever you are from, you can easily detect how strongly your environment has been changed. We intervene directly in the water cycle. We build the reservoirs, we divert the water, we use the water, we abstract water. Due to these activities, mainly due to changes in the vegetation cover, we observe land use impacts, something like erosion in many parts of our globe. But we use also groundwater systems. We exploit groundwater systems, even groundwater systems which have been formed over thousands of years are utilized within a short period. So all these changes have impacts on surface runoff, on interflow and on base flow, but also due to our activities, we change the vertical movement. We drain wetlands, we irrigate, so the evaporation pattern is being changed. All these vertical fluxes are also changed. How strong are these impacts? Well, it's surprising. When you go to the ICOLD database, International Commission of Large Dams, they have quite a huge database, but you should be quite aware. In the meantime, I would say more reliable databases have been developed, but I only could find there are very likely more than 1 million of dams with a storage capacity in total larger than. So when you compare that with the natural storage capacity on our globe, it's about 4 to 10% human activities. And inundated areas are about 2.5% of natural covered areas. And due to channelizing of our rivers, due to modifying the land use, we've also quite substantially modified the inundated areas. According to ICOLD, 50% of the dams are used for irrigation purposes, 25% for hydropower, 20% for flood control. More than 1 million of dams. What are the impacts of the reservoir? There is obviously a goal behind. So we need safer water provision. So during low flow periods, dams help us. They provide drinking water, they provide irrigation water. Dams are useful with respect to power generation. Hydropower, very essential, renewable resource. So it's interesting for us, it's useful. But we have changed the seasonal pattern due to our dams and reservoirs. We have changed the short-term cycles dependent on reservoir operation, etc. We have substantially reduced global runoff data, and this in turns has led to accumulation of sediments in the reservoir, and this has also impacted on flood storage capacity. But dams have also some disadvantages, and one of them is, on one side, dams help with respect to flood protection, but any structure, also dams, can fail. And here I've only listed a few examples about dam accidents, and here the number of fatalities. This happens everywhere. It happens in Europe, this happens in India, this happens in the United States. You find it really everywhere. Dams and levees can fail. So on one side, we reduce the variability or the frequency of flooding. On the other side, in the extreme cases, we increase the flood risk. Think about land use changes with respect to our environment, especially natural wetlands. They are responsible for water storage. They are quite responsible for recycling of greenhouse gases. I don't say today something about biodiversity, etc., but they are also quite relevant for our biodiversity indicators. An estimate indicates about 10% of the land area can be classified as wetlands, but they are under extreme pressure due to drainage activities, etc., due to agricultural activities, and there's an estimate about 33% of our wetlands have been lost already. Let's think about water management and water abstraction. This is discharge pattern annual flows of Colorado River at the southern international border, and the black, dark black bars here indicate changes from 1910 to about 2000. There is a clear trend, and more or less there are longer periods with no discharge at all of Colorado River. This is the reconstructed graph, how the discharge would look like without any water abstractions. So what we see here is not due to climate change, it's directly related to human impacts. Think about the Nile River in Egypt, at Aswan. Here you see time period from 1920 to about 2000. So this was the inflow of the Nile upstream. These are different locations. For each location, you have a different graph here. So this is refers to the period up to 1960, 1965. And then Aswan Dam has been completed, and there is a clear drop in the runoff for the period from 1965 to today. This difference here is due to water abstraction. It has nothing to do with climate. Irrigation activities. I've used only one example here, but you find it most dominant example, Lake Aral, but the same you find on Lake Chad, the same you find on Lake Urmia in Iran. Also, Dead Sea, wherever you go, all these endorheic basins. Disappearance of Lake Aral. This is a pattern of 1960, and this is how it looks today. So most of the former area has fallen dry, and only a few parts have remained in the north and some in the western part. But this large area has dried up. Main activities, water abstraction for irrigation purposes, and at the end, disappearance of Lake Aral, and the same happens in Lake Urmia. We were invited some about 15 years ago. We did a study with colleagues from the riparian countries, and also some colleagues, experts from Russia were invited. What could be done to rehabilitate the region? And in all of the different scenarios, it turned out only a smaller part in the north and maybe in the western part could be maintained. So these examples I tried to give here: Colorado River, Nile River, disappearance of lakes. This is due to human interventions. Climate may play also a role in all these examples, but a minor role. Similarly, direct human interventions dominate changes in the climate signal. So it's not the external processes that are modifying our environment in that period we are discussing. It's due to human activities at various levels. But we need to take some action. So one thing might be try to mitigate climate change. And you know about that. There are many international treaties, agreements to reduce greenhouse gas emissions. You know the recent status, not too much has happened. Mostly papers are being developed, but slowly it's starting that we try to adjust and to transform our system. Adapt to climate change is also a strategy we could apply, but the scope is also limited. So how could we handle that? And usually our design approaches are based, as I said, on observations of the past, and then we fit the model, then we apply it to the future. And this means we assume there is no change in the system. And I tried to show you a lot of things have been changed. And I've here only one example. For instance, think about demographic changes. And I used here an example from Austria. So all the colors which are red indicate it's a forecast, for the period of, what is it? For, I think, yeah, until 2030. How the distribution of population would look like. And you see, this is the capital. I'm living here, Vienna. So many people are attracted by the city, they will move here. The same holds for other larger cities. So everywhere you can see around the cities, concentration of population, and several areas indicated by blue, we observe a decrease in population. So this is an information that when you think about flood and flood impacts, well, we should be careful for the regions where we have more people in 20 years. The impacts, the damages would be larger, obviously. So I'm a little bit skeptical by using traditional approaches like a frequency-based approach. I tried to show you what will happen with the 100 years flood frequency in different regions of our globe. Be aware that our environment is quite shaky, and be aware that more or less everything is changes. So frequency approach, I thought that, I'm still thinking it has some benefits, but we should think about other approaches too. For instance, think about scenarios. Let's make assumptions. More people will be in that area, less people will be in another area. What would be the consequences for impacts? Okay. Assess the damage potential for different flood events. Assess the damage potential for different population densities. Assess the damage potential for different regions, etc. And somehow, this has been condensed, for instance, in the European Flood Risk Directive. Still, something can be criticized, but at least assessing the flood risk, elaborating flood inundation maps, management plans has to be repeated at a 6 years period. So every 6 years, we need to adjust our plans and we need to update that. And I think this is already a good directions to cope with a quickly changing environment. Scenarios. Another way would be use sensitivities. So what happens if a flood would be 10% higher? What happens if during vegetation period available water would be 10% less? What happens if a drought period is 10% longer? And we, based on such assumptions, we can test how our system would work, and we could identify somehow threshold levels when severe problems would pop up. It has not too much to do with probabilities, but we can learn how sensible our human-made system is based on changes in precipitation, runoff, temperature, etc. In another project, I will explain that in one of the next presentations. I think it's in June. We used also scenarios for assessing the reliability of water supply systems for larger parts of Europe. And development scenarios are available. We did not develop them, we used them. And there is a list of 5 scenarios which has been developed within the Prelude project with quite different strategies. I don't want to go into detail, but you see here a graph with 5 directions characterizing, let's say, the level of our society. So environmental awareness, solidarity and equity, governance and intervention, agricultural optimization, and technology and innovation. And here these scenarios put the emphasis on different aspects of this general development. So here the impact in that scenario would be on technology and innovation and agricultural optimization. And here the impacts would be on environmental awareness, solidarity and equity, etc. And then we can study what would happen if. So, coming to an end, what can we conclude from these brief outlines? Obviously, we live in a very dynamic environment, driven by climate change, but also driven by population growth and migrational patterns, and this results in drastic land use changes. And all these changes are very often neglected, as I tried to say, looking back, analyzing data, fitting a model, applying it to the future. Going into more detail, our water balances are strongly dependent, obviously, on climate variability. Our water management structures are based on time horizons of about 100 years. Design levels refer to estimating indicators, design values for a period of several thousand years. This means we are entering already the scale of ice ages. And additionally to probabilistic-based approaches, I think we should put more emphasis on scenarios. We should also think, I did not touch this point today, about ecosystem services. And this would help, I think, that would additionally help in managing the future systems. As I tried to explain, what we observe in greenhouse gases today exceeds all what we have, what has happened in the last 800,000 years. And the Milankovitch cycle are the main drivers for glaciation and the cyclic behavior due to the orbit of our planet influenced by other gravitational forces. And we have a lot of internal feedback mechanisms. They will also be changed due to these external forces. And in planning, we face to cope with trends and cycles, and I briefly tried to present some ideas how we could more realistically tackle our future. Thank you for your attention. Nobody here?
Thank you, Professor.
Yes.
Yeah. So now we open the forum for the questions. So for the questions, I request to come forward. Anybody? Yes, please. Any question? Oh, yes. Some people are writing on in the chat box. Okay, fine, but please.
Yes, one second.
Raise some question. Yes. Was it too technical or too very?
Okay. No questions.
Professor Gabriela, are you here?
Yes, I'm here, Professor Hazrat. Well, I would like to congratulate Professor Hans-Peter for the presentation. It was wonderful. Yes, it was technical, but very interested for us. Thank you very much for your time.
Thank you. Thank you.
So, Professor, Professor Gabriela, please conclude and yeah, please do.
Sorry?
You are requested to conclude this lecture. Conclude, I mean, just close. We are going to close it, okay, now.
Okay, do you want to conclude the presentation of Professor?
I request you if you can.
Okay, good, okay. So it was really interesting, in special because we are speaking here for natural resources management and ecosystems, biodiversity, and of course the details presented by Professor Hans-Peter are included in this big science related to natural resource management. I think our attenders was captivated by the presentation, especially because I think we are all specialized in this field. So each detail and each information are very useful for everybody. I'm sure that all the presentation during in this program of global lecturers are are interested, and it is a big experience and wonderful experience for each of us to attend of these programs. Thank you, Dr. Hazrat, for your wonderful and amazing implication. And this energy which keep us connected with Grassroots Institute, with your activity, and why not keep us connected together. And thank you all.
Yes, sure. Thank you so much, Professor. Yeah. Yes, it is a kind of overdosing also, because sometimes parallel communications float and some people really hang. So anyway, yes, I think on Sunday you will be with us, okay?
Yes, yes.
Yes, on the Sunday at 10 o'clock, 10 o'clock.
I will be here.
Central European time, yes.
Yeah,
So,
I'll be here.
yeah, Professor Hans Peter, your lectures will be, next one is on 3 June.
Yes,
And another is on 15 June.
yes.
So I request you that we want to change the time, shift from 10 o'clock to 4 o'clock, 4 p.m.
Let me see. But we can discuss, should we discuss it now if you want me?
So if you give me the hint, then I will change the data.
Same day, but different time, you said.
Yeah, only the time change to 4 p.m. Reason being that many people have this official time. This is the working time in majority of the.
Yeah.
Yeah, this 10
Yes, a
o'clock.
third would be okay.
10 o'clock does not suit to many people who are attending the lectures or attending or lecturing in their respective universities. Many are the students who are not able to attend our lectures because of the time clash.
I understand. Yeah, but on 15th of 3rd of June would be okay. 15th of June, when we start at 4, yes, it's also possible. Yeah.
Yes, sir. Yes,
But,
sir.
yes, yes, both dates are okay.
It will be great. I mean, thank you, sir. You have cooperated. Yes. But on Sunday, the same 10 o'clock is fine because that is the holiday. So, Professor Gabriela, we hope that you will have quite large number of audiences.
Yeah, I hope so.
Yes.
I'm prepared for every surprise. But I think I will have attenders. Some of my students, my colleagues, we will see.
Okay, thank you, sir. Thank you, madam. Thank you, everybody. So we close this session. Thank you.
Okay, thank you. See you Sunday. Bye.
Thank you.